Okay, so recall that last time we defined the following to mean the control knot. So if we have two quantum wires and this, then this was the C knot gate and its output here, nothing changes here. Actually, and here I get, I'm going to write it like this and then define what this means. This is just going to be A plus B mod 2 from now. Okay, so I'm not sure if I used that notation last time. So just to be clear, this was what we saw last time. So this is just an A up here. This doesn't get changed. And here we add on A. So this was our, I think, the only quantum game we saw last time. So now I'm going to introduce something new, which is going to be another unitary 2x2 matrix, which we are going to become very fond of. And this is called the Hadamard. So this is, there are various H's, and usually it's clear which one it is. This is the Hadamard H, and H is going to be defined by this matrix. As a matrix, it's going to be the following. This, which you can check yourselves, is a unitary matrix. So if you do H Hermitian with H, you will get the identity. So that means that, because we will be using it, just recall that our what they call the computational basis, our basis with 0 and 1, kept 0 and kept 1. So H, this will be the first column here. So we just get 0 plus 1. And H of 1 is 1 over root 2, 0 minus 1. These states are so useful that we give them their own labels. This is defined to be plus, and this is defined to be minus. Okay, so they will come up again and again. Right, so you will see us at various points during different topics. We will have to compute what happens with certain circuits. So let's start with a nice easy one and see what happens. Let's see what happens if I put an H here on the first wire, and then we do a C naught. Okay? Now we're going to calculate what happens here in this circuit. Well, let's just start off with, let's say it starts off in 0, 0. And this is the way I like to do it. So what I generally do, and lots of people do these things with matrices and stuff and try and do it with the matrices. I find that quite difficult. So what I do is I do it with each individual basis element. So we've got two inputs here. So I'm imagining they're both 0. So we've got a 0 coming in here and a 0 coming in here. And we're Hing the first one. Okay, so this goes to plus 0, which by definition is 1 over root 2. And now I'm going to get 0, 0, and then 1, 2. Okay, so this plus, if I substitute it here and expand, I get 0, 0 plus 1, 0. So this is when I do the H. Yeah? So this is the step 1. This is putting the H. And now I do the C naught. This will be the C naught. And, well, the C naught, it only changes the second bit, flips the second bit if the first bit is 1. So here it doesn't do anything. And here it flips the second bit because the first bit is 1. And this, did we mention this last time? I think we did. So we did, yeah, so we mentioned this last time, so this is the bell state, and we noted it's an extraordinary state because we measured the first state. Given when you learn the results of measuring the first bit, you know exactly what the second bit is in. So this is going to be our, what I'm going to call beta 0, 0. And then the output of this, so one of the exercises this will be to count beta xy when you've got x coming in here and y coming in here. Okay, so that's one of the exercises. And then you have to do a little bit more. So we're going to use beta 0, 0 in the following system. Now, I wonder if I can, if I can put it down here and then we'll work it out up there what happens. Okay, so this is going to be our teleportation circuit. We're going to have 3 qubits. I'm going to break that one in here. There's going to be a handle here. This is coming along here. So the symbol for measuring is this. Okay, so that just means measurement. So this is measuring the computational basis, so we'll just get a 0 or 1 when we measure those things. And then when this comes along here, this is now giving us a classical bit. Okay, so once we do this measurement, this is either now after this, it's either 0 or 1. It cannot be in superposition anymore. So we denote that by a double wire. Okay, so double wire here. And then a double wire here. Is that? Okay. And what teleportation does is, well, it depends on these measurement results. So let's call this one M1, M2. So we only, I think I way down this. So this will be M1 and Z. Okay, so let me explain a little bit what's going on here. So down here we're going to put in beta 0, 0. And the point is that these 2 entangled qubits here, the second and the third wire, we're going to separate, physically separate. Okay, so one of these, I'll do that piece more. So these first 2 wires are going to belong to Alice, and this third one belongs to Bob. Okay, so what happens is Alice and Bob years before prepared and entangled bell state beta 0, 0. Okay, so here we have a beta 0, 0, and now that years later, Bob is somewhere else. And Alice wants to teleport. So this is Alice's state here. Some quantum state belonging to her. So this is Alice. That's this one and this one. and both has this one. Alice wants to send this quantum state psi to Bob. Okay, so years later, Bob is somewhere else, and Alice prepares a qubit. Right, and she will instantaneously teleport it, because if we follow this circuit through, let's see what happens. Okay, so let's say that this psi is A0 plus B1, and recall that beta 0 was 1 over root 2, 0 plus 1. So let's see what happens. So we start off in the state psi. Well, let's say it's beta 0. And oh, missed that one thing. Okay. So this is starting off in 1 over root 2 A0 plus B1. And the first thing we get to is a C0 gate. Okay, so this is depending on the first qubit. Second qubit will flip if it is a 1. Okay, so the first qubit here I've got 0. So this will, let's do a little arrow to indicate this first step. Let's do that. So this will go to 1 and root 2 A0. I don't know if I want to combine them now. I don't have one in minutes, so probably not. A0, 0, 0, 0 plus 1, 1. And now when I expand this bracket and I've got a 1 in the first qubit, when I do the control not, that's going to flip the second qubit. So I get 1, 0 plus 0, 1. Okay. Now the first qubit gets hit by a hammer, so this is now going to go to 1 over okay, so the only thing I did there was I applied the Hadamard to the first qubit, so the 0 goes to 1 over root 2, 0 plus 1, and the 1 goes to 1 over root 2, 0 minus 1.
Sorry, can you repeat what does this product mean, like between C and beta 0. What does this mean? It's not like that product, or I don't understand what you are doing here.
Wait, here?
No, well, yes, this. I don't know what's between C and beta 0 down.
And this is okay?
Yeah, but
But this is not.
This line. Yeah, this line, I don't understand what are you doing.
This is the 3 qubits. This is the first qubit. Okay. This is the second qubit in the second position, and the third in the third position is the third qubit. Okay.
Okay, it's because this is a matrix. Like, sort of.
It's a tensor. It will be a tensor.
Okay.
I'm being a little bit informal at the moment because I want the tensor product space to come out naturally when we get to the bit on the quantum mechanics. So for the moment, we can just think of it as it's the 3 qubits. Yeah, this is the psi qubit, and this is 2 qubits which are entangled. Okay.
Okay.
So the position, if I write them out as a triple, and into this, then you will see this is the probability, almost probability, A by O K conjugate divided by 2 will be the probability of being in the state 0, 0, 0.
Okay.
Yeah, we're all in 0.
Okay. Okay.
Yeah. When we measure. And then this will be A 0, 1, 1 plus B 1, 0, 0 plus B 1, 1, 1. So what you might, you can think of it as the matrix, or you can think of it, would it be a 2 by 2 by 2 matrix, which is the real matrix, it's a tensor. Yeah, you've got the dimension of the vector space, if you like, is 8. You've got 8 possible states in the computational basis, and these are the coefficients. But it was a very, very good question to ask, because now we do the thing that makes this clever, which is we use that structure. Now we're going to suddenly switch this round and try and write this. How would this be as 1/2? And I write now with the first 2 and try and bracket out and write it the other way. So where do I get the 0, 0 from? The 0, 0 come from this, when I expand out these 2 brackets, and I get a 0. Here I get the 0, 1, here the 1, 0. Here's the 0, 0, and it's for the plus, so I get plus 1 here. And if I wanted to do
and A and B, you're missing A and B, right?
Oh, yeah. Missing A and B. Right. Thank you. And if I was to do 0, 1, then I'll get again A 0. Oh no, I get an A1. So the 0, 1 here gives me a 1 there, so we get A1. And 0, 1 here is a plus B0 plus 1, 0. And 1, 0 gives 1, 0 would be A0. And then I guess it's going to be minus. 1, 0, there's a minus here, so it'll be minus 1. And 1, 1. Where we get A1, and then 1, 1 minus B0. Okay, so that is the current state when we get just before the measurements. Okay, so now it is.
Wait, are we missing a letter on the third term? Or
yeah,
1, 0? Oh, okay, that looked weird. Okay,
thank you. So now Alice has in her possession these 2 qubits. Okay, so she could measure these 2 qubits. So now Alice measures her. If she measures 0, 0, she tells Bob to do nothing because if she measures 0, 0, then Bob's state is precisely this. Which is psi. If she measures 0, 1, she tells Bob, apply, now, she's got this state, so apply Z. If she measures 1, 0, she tells Bob, apply X. No, apply. Oh no, sorry, apply X here. If she says 0, 1, we want to switch to the 0 and 1, so we want to apply X. If it's 1, 0, then we want to apply Z, and then Z, recall that Z has this as a matrix is 1, 0, 0, minus 1, so it has this action. And if she measures 1, 1, then she tells Bob to apply X and then Z. Okay, and if you apply X and then Z, of course, you will take the 0 and interchange the 0 and 1, and then change this sign and get back something. In each case, then, and that's what I mean by this circuit, the end of this circuit here. So this graphical wire is passing a piece of information, that's the result of M1 and the result of M2. And if it's 0, then this is the identity, and if it's 1, apply X. So it's just a fancy way of writing down what I've written here in words. Okay, so that's just that done as a circuitry.
But you are doing like if to the X to the M power enters a 1 in them, we applied like X will be applied if a 1 comes through the top.
Exactly.
And this is like linear.
This should actually be the other way around, shouldn't it? Because this is the first qubit, this is the second qubit, so it would make more sense to do this way around. Sorry, say again.
So this is a linear transformation of the qubit of Bob and M2.
M2 is just a number. M2 is just a number.
Yeah.
0 or 1. Okay?
Yeah.
So, and so is M1. So when Alice does the measurement, she gets this would be M1 would be 0 here, and M2 would be 1. Okay, so this is 0 here, which means Z to the 0 is the identity, and X to the 1 just assumes X. So what happens is Bob applies X.
But this transformation, like you are, the qubit of Bob is changing.
The first qubit?
No, the one of Bob.
Bob. Yeah, it changes. So he applies X.
And this will be like linear in, like.
X is this matrix. It's just in the ellipse. It goes 0, 1, 1, 0. So it changes X to 0 and 1.
Yeah. Okay. Yeah.
Yeah, it'll be linear because it's a matrix. It's just a matrix. Okay? So whatever the result of this measurement, and look at each of these, so Alice will measure each of these possibilities with probability 1/4, half times 1/2. And whatever the result, she can then tell Bob what to do. And she can phone them up and say, oh, yeah, I've got 1, 0, so I want you to apply Z to your qubit. And even though he is somewhere else, he will suddenly have in his possession this psi qubit that she prepared for. Now that's almost faster than light. I mean, that's almost speed of light. I mean, it would be instantaneous. The only problem is she needs to pass that classical information to Bob so that he can then know what to do. Okay, so that's the only thing that's stopping it being faster than light. Now this seems like a little bit way out there, but this experiment apparently was successfully carried out in 2012. I'm just going to read this because I'm not sure I understand all the words. By the Austrian Academy of Sciences, teleporting a quantum bit over a distance of 143 kilometers from La Palma to Tenerife. In fact, due to the atmospheric attenuation, the gradual loss of flux intensity, there's a noticeable loss, and the success rate was only 71%. But that's much better than 50%, which it would have been if there was no entanglement. Okay, so it's evidence to this to suggest that this really does work. Okay. Yeah, so I think the important thing to get here is probably what Paula said. Paula said that here, like, kind of, what is this notation meaning? Okay, that's probably quite important. That there's an order here, and when we see the order of, you can read them like together, and that's the qubit order of the actual qubits. Okay, so that's probably the first time we've really seen that at work. Right, so that's quantum teleportation. Now things are going to get even weirder. Okay. So 1.6. This is going to be a little bit of a taste of what's to come in quantum algorithms when we will look at basically the known quantum algorithms, which at least when Nielsen and Schwang was written, and I still believe is the case, there were only really 2. And they kind of, we'll see simplified versions of one of those today. Okay, so now, yeah. Well, the first thing that I have to tell you is that quantum gates are always reversible. Okay, so that's kind of what we saw last time with the unitary transformations being like preserving the probabilities and therefore having an inverse. The determinants are definitely non-zero. So cannot directly So some quantum gates in general are not reversible because often they just take two things to one thing. But we can get around this by using what is called a Toffoli gate. So the Toffoli gate can be replaced. And this Toffoli gate is like the C naught, except that it's on 2 qubits and not just 1. So there are 2 control bits, and then here we have our C naught. Okay, so by definition, this means if we have A, B, C, A is coming out here, B is coming out here, and this is C. And you need both the A and the B to be 1, otherwise you don't do anything. Okay? Now, it's one of the exercises to show that all logic gates can be replaced by these reversible Toffoli gates. I'll do a couple of the easier ones for you. The first one is kind of like straight away, so let me do that one. If you have X coming in here and Y coming in here, and you start off with 0 here, then you have X, Y, and X, Y. So this is and. Okay, so there's and I'll do one more for you because this is an important one. 1, 0. So 180 would be 0 plus 1 times 1 times A, which is A. Okay, so here this is fan out. Okay, so this is fan out. And part of the exercise is to prove, of course, that this is a reversible quantum gate, and the hint is that you can easily find its inverse. Okay, so that's a gentle hint for this. So this is a reversible. This is reversible. Okay, so we need to add an extra qubit, and then we're able to implement any classical circuit. Well, it seems like I'm going to do a lot of effort just to be able to implement classical circuits on a quantum circuit. But as we shall see, almost very soon, this is extremely strange. So just consider the following. So we consider the following. Considering the function f. For the moment, I guess let's just do it from 0, 1 to 0, 1. Okay, so let's just got some function which we can compute on a classical circuit. We will use this notation to make this into a quantum. So this will be this. And as we've seen, we can, so this is the definition of UF. just seen, if we have a classical circuit for computing this function, then we can stick it here on our quantum circuit. Yes. So the fact is, like, we can stick. We can. Thanks. Okay, so yeah, still doesn't quite see what's the point of all doing this, but now we're going to do something a little bit strange. And this somehow is a little bit tricky to get our heads around. We can put into this circuit, instead of just putting in 0 to 1, we can put x, for example. What happens if we put in x as a superposed state, so 0 and 1, and y is equal to 0, then this is, so we put in, so we start off with 1 over root 2, 0, 0, plus 1, 0. And pen it's running out. And we stick it in here, and this goes through the UF, the x doesn't change. So here we get 0, and here we get y, which is 0, plus f of 0. So we get f of 0. And here we have 1, and here we get y, which is 0, plus f of x, which is 1, so it's 1. So what you should be worrying about now is, like, did this really just calculate 2 values of f just with 1 call? I mean, couldn't we push this further? Couldn't we now put in, what happens if we have a function from so now let's have a look and see if we have, so now consider a function f from 0, 1 again to 0, 1. And here coming into this, we're going to have not just one y, but n y's. So we have n y's coming in here. They hit this UF. This is all going to be x. So this is belonging to 0, 1 to the n. And here we have x coming out. And here we have. So what would we want to do to simulate this superposition here? What would happen if here, for example, to feed into this x, I started off with zeros everywhere, and each bit we apply a Hadamard. Oh, so here we have, when we apply a Hadamard So if we apply a Hadamard to each one of these before, if we start with more often 0, apply Hadamard to all of them, what we end up with will be our first n bits. So this we can write into. So I am going to introduce the tensor notation without actually telling you what a tensor algebra, tensor space is yet. But and now we can apply the Hadamard n times, and we end up with 1 over 2 to the n divided by 2, the sum of x. Okay, so x is going over every binary string of length n. Okay, when you multiply out all these brackets, you'll get every single possibility. So then we feed it into UF, and what we end up with is the sum. So the output from this is this. If we could, if I've used a different x here. It's just one to the n. Well, this is in 0, 1 to the n, so that's okay. Yeah, okay. So put in. And sometimes you should be hopefully screening.
Is there a reason why we separated them here and put them together, like in the first row, like before?
No, you could just well write this as x equals x.
It's the same, right? Or is there a different? Huh?
It's exactly the same, yes.
Oh,
yes.
okay. Yeah.
Okay, so I can also write that as this. Sometimes it's just more convenient just to see it, yeah? Because otherwise, maybe this is x times f or something horrible. But yeah, no, it's just because I had the x0 here to differentiate the fact that x was running through, but I thought it was probably more clear to write it like this, but no, it would be the same.
Yeah, I don't know. Like it might be like it's the I think also it's also clear that you don't think they could be multiplying each other. It's just because before we put them without separating them, but yeah, I think like the bottom one is better.
This one better.
Yeah, no. But what I was before separating them.
Separate. Anyway, so this is the output. So something should be screaming here because like we've just applied one thing on our circuit, and all of a sudden we've calculated 2 to the n values of f. Now, this is a kind of a quantum leap of trust in quantum mechanics that this actually happens, and maybe it does, and maybe it doesn't. It doesn't actually matter whether nature really calculates all these 2 to the n values of f or not. What matters is that because we don't know, and we can't see it until we ask it and measure it. Okay, we measure it, we get a result, and we've only got like one value of f. So, yeah, has it really calculated, or does it only calculate it when we ask it, when we measure it? I don't know. We don't know. So, so if we work out on the theory that this is somehow the state we have at the end of this circuit, everything works. And experimental data backs you up that this works, as we are about to see in our next algorithm. Well, we haven't seen an algorithm in our first algorithm. Okay, so now we're going to have a look at two algorithms. One which is based on just when n is 1, and then we'll switch to the general case with the n. But I wanted to show this first, just to show you that it's kind of important to start getting accepting the fact that we have these things which can, these quantum gates which can perform apparently amazing things. Okay, an exponential number of calculations in one go. Yeah, so having that exponential. So warning. Then we obtain one value when we measure. Okay, so it's not it is amazing, and it will be amazing, but it's not quite that easy. It's not just that, oh yeah, we can suddenly like do an exponential number of calculations in one step. We can't, because we cannot access that information. Run out of pen. Now, this is here's an example of an algorithm. This is the first one. We're going to look at two now. And I want to change back to this code trees. I have to quickly change that. So the feed in 0 here. Okay, so also we're getting more and more used to calculating quantum circuits. That's good. So this f now is again just a function from 0, 1 to 0, 1. Right, well, let's see what happens. So we start off with 0, 1, and we apply h to the first one and h to the second one. Yeah, so this is the two pattern marks, and this is half 0 plus 1, 0 minus 1, which is equal to 0, 0 minus 0, 1, plus 1, 0, minus 1. Okay, so we're now comfortable with doing things like this, and now we're going to apply UF. So this is the H's, and now UF. 0 plus 0 minus 0. So we're going to get f of 0 plus 1, which can I write this for a not? Okay, so this should be good. Well, I could do plus 1, I suppose. That's 1, 1. Now let's just analyze each of the 4 cases here. So let's just say if I'm going to do this in a strange order just so you can see it a little bit better. Okay, let's just see what happens this if we have 0, 0. This is oh, I forgot. Oh, sorry. I forgot the last command. So the last command then gives 1/2 root 2. And this is going to be oof. Okay, naught. So I've got to apply the Hadamard to the first, just to the first qubit. So this is going to be a 0, 0 f of 1, and now we're going to have minus 1 f of 1, and the final one is a minus 0 f of 1 plus 1, and then I get minus, so that's plus 1 f of 1 plus 1. Okay. Oof. So this is all my states. So what happens if f0 and f1 are both 0? I have a 1, 0, 0, 1, 0, 1, and a minus 1, 1. But here I have plus 0, 0, minus 1, 0, and I had a plus 1, 0 here, so these two cancel. Minus 0, 1. So I've got that twice, and now I have a plus 1, 1, and a minus 1, 1. So the ones that came twice are this one and the 0, 0. So this would be 1 divided by root 2 times 0, 0, minus 0, 1. Okay, so this was the one that was getting repeated here. Okay, so it's just, and I will write up what the other ones are, so you do it in the same way. You just substitute in these values, and you get these results. But this is quite remarkable because in the second bit, you've nearly always either got 0 minus 1 or 1 minus 0. And in the first qubit, you've always got f of 0 plus f of 1. So this is plus or minus f of 0, f of 1 in the first qubit, and in the second qubit, you have 0 minus 1. Okay, so this first one, divided by 2. Okay, so let's just go through and check that this is true. So what I'm saying is that this first qubit here, if I add up f of 0 plus f of 1, modulo 2, I will get whatever's in the first qubit. So let's see if that's true. That's 0 here, that's 0 here in both cases. It's 1 here in both cases, and it's 1 here in both cases. What so I could, if you like, factor out that first qubit, and then the second qubit I get 0 minus 1, 1 minus 0, 1 minus 0, 0 minus 1. So it's plus or minus, which I can also take out, 0 minus 1. And the idea now is to simply say, measuring the first qubit, we get with certainty f of 0 of 1. Why is that interesting? Well, because if you want to calculate this on a classical circuit, you'll need to do two. You'll need to do two operations. So in one operation, or one operation F, in one application F, albeit on a superposed state. I say application F because it's really UF. Okay? Whereas if we want to calculate f of 0 plus f of 1 using a classical circuit, we have to calculate f twice. Okay? Small gains, but important gains. Okay? So just with this algorithm, they knew something was up. Yeah? Something here that we can do on a quantum computer, and we cannot do it on a classical computer. Is that okay? Yeah. Right. So you're probably not that impressed with that. But I hope you will be impressed by the next one. So that was the Deutsch algorithm. It's worth hearing these things because when they talk about the latest implementations of quantum computers, you will hear a lot the words Deutsch algorithm, the Deutsch Josa, which is the one I'm just about to present, and quantum teleportation. These things are absolute, if you like now, classics of quantum computation. Okay, so here's another example. This is the Deutsch Josa algorithm. And once again, I have a little bit of historical information for you. This was implemented on an iron trap. We'll get a little bit, we'll talk a little bit for a while about how to, possible ways to make a quantum computer. But an iron trap is one of the most common, in 2003, okay, by Gouldet, can't read my writing there, Rubik and Lancaster. Okay, so now we've gone back to, okay, again, we've now gone from 1 to n, so now suppose we have an f from 0, 1 to the n, to 0, 1. Which, and we know something about this f. Imagine that we know it's either constant or balanced. So constant means it's either always 0 whenever you evaluate it or always 1, and balanced means 50% of the time f of x is 0 and 50% f of x is 1. Okay. So how many times do you need to evaluate f to decide whether it's constant or balanced? So we need to evaluate 2 to the n minus 1 plus 1 values to determine which is this. Okay, so to determine whether it's balanced or constant, you have to go through just over half the values, because up to half the values, if you've got 0 every time, well, it could still be, it could in theory still be the balanced one, or the higher unlikely. But to be sure, you have to do half of them, then plus 1, and then if you get 0 again, you know it's constant, and if you get 0, if you get 1, then you know it's balanced. Okay, so now, I've given everything we've done so far. I think it could probably almost leave this an exercise, but let's draw the circuit which will allow us to determine whether this function f is balanced or constant. And they send the book with one, well, it's one application of f, but you do actually have to do any measurements. So, I'm sure it's one really. So here's the circuit. So I'm going to, so we have n things coming in here. So all zeros. And we have from all. So this is as we did before. Here we do something slightly different. We're going to apply x, then an h, and then feed in. So this is going to start with 0. Then we're going to do okay. So before we actually try and do it, let's do this in stages, because it's there are basically two things that we have to do here to work out what. So the question is, what comes out here? Okay, so that's what we want to work out. To do that, I want to, yeah, so well, we already did this bit, right? So we did this tensor n times, and we applied the h tensor n, and we know that that went to all the x in 0, 1 to the n, 1 divided by Okay, so that we already that bit we already did. This bit, let's see what happens to the last bit. So this is going to get to the x, is going to go to a 1, and then the h is going to go to a 1 over root 2. I've got loads of pens in the lecture. Stop that before next week. Right, so we're going to be applying UF is going to be going on to, oh, that one's moving on. 1 over, so let's put these two things together. It's got root 2. So that's what's coming into UF, and now we're going to apply UF. Yeah. So, well, okay, we probably want you to actually just leave this and do it separately. I'll tell you why now. Okay, let's just leave this. Let's take this out. Now, what happens if f of x is equal to 0? If f of x is equal to 0 when we apply UF, this doesn't change. Okay, it's just 0 not minus 1. What happens if f of x is 1? Then we add on, so if f of x is 0, then the 0 minus 1 point goes to 0 minus 1. And if f of x is equal to 1, then 0 minus 1 will go to, well, we're going to be adding on 1 here, so this will be 1 minus 0. Which of course is minus 0 minus 1. Okay, so when we apply the UF, we add on f of x here. If f of x is 0, nothing changes. If f of x is 1, then this changes to a 1 and this changes to a 0. So all that happens is the summing changes. So really what we get is the same thing. Okay, and realize that this is not an overall phase. This is dependent on x. Okay, so it's not that I'm taking out of the whole sum. So it's very, very relevant. This is what's called phase kickback. Now, let me just take this out, because what we're going to do now is apply the Hadamard n tensor product n to this x here. So let's just do that apart. So how would that be? So h tensor n to x1 up to xn, so writing out as the binary string. How will this be then? Well, this x1, h of x1 is going to go to let's think, that's going to be 0 plus minus 1 to the x1 times 1. Okay, because if x1 is 0, then this is going to be a plus, and if it's 1, then it's a minus. Okay, so this is going to all to the all together ones. So we get 0 plus minus 1 to the xn 1, which we can write again as the sum over. Yeah, so this will be the sum over z, and 0, 1 to the n. How many z's do we get? Well, why have I got the? Oh, because that's from 4, is it? Oh no, of course. Yeah, when I apply the hammer, I get a root 2 every time. So I've got to, again another 2 to the n divided by 2 here. So there's a 1 over 2 pn divided by 2. And here I've got to work out how to the signs. Well, the signs depends on how many ones the z's and the x's coincide in. So this is going to be minus 1 to the x scalar product z. Well, this is just the standard scalar product between two binary strings of length n. Okay, so that's what this is going to be. Yeah, because if z has the 0, then you just take the 0 here. And if you take 1, it depends then on what the sign here is. So at the moment we're down here, and we are just going to so now we can apply our final h. So now this is our final n, which we've just done. So we've got 1 over 2 to the n, so 1 over 2 to the n, 1 over root 2. And then the sum. And now we're going to get the sum over x and z. 0, 1 to the n. Minus 1 to the f of x plus x dot z, z. And in the second bit, still the 0 minus 1 in the last bit here. So this is just corresponding to this qubit here. Right. Now, what happens if we measure the first n qubits? Well, we're going to get each one of these possibilities z with a probability depending on its amplitude, or what we would call a coordinate. Yeah? So depending on what the coordinate is, so it would be a bar, depending on what this a is here.
Can you repeat that again?
So now we're going to measure. So we're going to measure the first n qubits. Okay. So let me write that down. Now measure. And the probability, well, the probability of measuring this z, yeah, so this z in 0, 1 to the n, will be precisely its coefficient, which is the sum over x of this thing. Yeah? So maybe it'd be better to write Z mix in the other way. Not that it makes a difference, but so there's double sum. So the probability of measuring x is its coefficient times its conjugate, complex conjugate, where it's a real number, so it will actually just be itself squared. And what happens? So what is? So we will get. So if we will. So if Z has coefficient A, then we measure Z. A. Okay, so that was just what we saw earlier in the week. Okay, so what is the coefficient? But what is the coefficient? But if f is constant, coefficient of 0, 0, 0. So Z, the binary string of length n with all zeros, that's 0. F of x is constant. Summing over all the x's in 0, 1 to n is 2 to the n. 2 to the n divided by n is 1. Well, yeah, you've got the root 2 from that, but it doesn't. Yeah, okay. Yeah, so it's not the 0, 0, 0. This is 0, 0, 0, 0, 1, 1 over root 2, 0 equals 0 equals 1. Okay, so the only term, so we will get this with a probability of 1. So we will measure it, so we will. Okay, there is no other possibility. There isn't, because we know that some of the probabilities is 1, so it's all there. And if f is balanced, then what happens to the coefficient of 0? So the terms. Well, if it's balanced, this is again 0, because this is all zeros. So we're going to get 50% of the time 1, and 50% of the time minus. So they add it up, we get 0. So they have coefficient 0. So if we measure it and we measure all zeros, we know f is constant. If we measure anything else, we know f is balanced. So if we measure we know is it balanced because it's impossible to these coefficients here, 0, so it never collapses to one of those. Brilliant. Isn't that amazing? So in a way, I mean, it's almost like an exponential speed up here. So I mean, this would be the dream of quantum computing, is that we can really run exponential time algorithms in polynomial time. And this is slightly deceiving, but anyway, it shows that there are certainly problems which are more suited to quantum circuits than classical circuits. Yeah? So this, as I said, this has been implemented with success. So it really works. You can determine these properties like this of F. And I wrote an exercise which I made up myself, so which is along the lines of this one. So we shall have a look at that next week. So talking of exercises, what's the time? 3:30. How would you like to do it? Do you want me to just randomly decide who does what exercise and I'll send you an email, or have you had a look at the exercise and think, oh, I'd like to do a certain one, and then you suggest to me and I start writing down, or should I just like randomly? Okay. So maybe I will just start. I will send out an email tomorrow, and you can have them over the weekend. Okay, so I'll just send an email tomorrow with a distribution of the exercises, and hopefully we can get those done. So I should think we could probably, if you have anybody has this ready, what we could do is mix up the 2 sessions next week, do some of the exercises and some with some theory. Okay, so we can mix and match, and it's probably better than trying to do an entire 2 hours of exercises. I'm trying to decide what to do, whether to have a look at the exercises now and see if I can give some hints, because some of them are quite long. Or whether to continue with the theory. What would you prefer? Would you prefer to have a look at some of the exercises now, or should I leave you to have a look at them over the weekend and I'll continue with the... No response. Okay, well, maybe I'll leave them now. We can go through this. You can have a look at them first. Let's continue. Okay, so now I'm going to talk a little bit in 1.7. This will take us to the end of the introduction about complexity classes. And obviously, we need to talk a little bit about as we saw in the previous exercise, what how much maybe time or how much space certain algorithms require to run. So a very useful notation on that, which I'm sure you've probably seen before, but let's just make sure, is the following. We say two functions f is in big O of g, if it's a constant and then not such that for all n bigger than naught, f of x is then bounded by this constant times gx. Okay, so that's just how we have introduced how we define the big O, and then we have little O. We say it's a little O if for all C
Sorry, do you mean n with instead of x?
Yeah.
Because then okay.
So the idea being, in this case, is basically the quotient tends to come to 0, right? You can choose this C as small as you like, and f of n divided by g of n is going to be very small. So let's just give us an idea. So I can just talk about what different complexity classes. Okay, so a decision problem is one that has a yes or no answer. So, for example, asking if a number is a prime number is a decision problem. It's either yes or no. Another famous one would be Hamiltonian. Now, this is not a Hamiltonian that we will see later in Schrödinger's equation. This is, does the graph have a Hamiltonian circuit, which means circuit so just so, for example, this graph here. Oh, that's not very good. This graph here doesn't have a Hamiltonian circuit. Just if you well, it doesn't, yeah, because you can't get back there. Let's see if we can try and make it a little bit more. Anyway, so this one doesn't. Okay, so this is these classical problems. So loosely, I'm going to define some complexity classes. Now, really, I should be a little bit more formal about this. But let me just write this. So a problem is in time Fn. Okay, so we're saying something is in time Fn if it can be solved in big O Fn operations. Now, these operations are on a Turing machine. So these operations are on a Turing machine, which is an infinite tape. Going to one direction. A tape-out program, and if I really get into the details of defining all of this absolutely rigorously, we're going to be here a long time. Programming, etc. So I'm going to cheat a little bit because we have a lot to get through, and I think for those of you that already know about it, one of you will already know some of this before. Those that haven't, I would ask you to have a look through chapter 3 of Nielsen and Chuan, and that certainly has enough of what we will need. And as I say, really what we want to do is like just look at an algorithm and say, what f of n is this? Yeah? What complexity class here? How many operations do I need? And that will effectively be enough for us. Yeah? We want to know, is it exponential, is it polynomial? And doing it all very formally and using the language of language. So from computer science and Turing machine is not going to be exactly helpful to us. So I think it's enough for us to have just an informal idea of looking at an algorithm, working out how many operations it is. What is important is to know exactly what this little n is. Okay, so little n is equal to the number of bits in the input. Okay, so that's kind of important. So in this prime example, to input your capital N, you need log n bits. So n is log n, log 2n. Whereas here, so for a graph problem, n is about n squared, because I have to tell you for each one of the n vertices whether there's an h between the two. So that's a 0 or a 1. Okay, so it's roughly n squared. Choose 2 plus n minus 1, so we choose 2. To define the graph. Okay, so that's how you that's the n here on that we're interested in, and that will be important for us. So the first complexity class I want to talk about is P. So these are the decision problems So this P is for polynomial because they are problems which can be solved in polynomial time. Now, of course, so in 2000, so what we want to know is where these different problems are. And in 2006, the problem prime turned out to be an element of this P. Okay, so this was suspected but not proven. And that was an amazing achievement. So to find a polynomial time algorithm which allows you to decide whether this capital N is in P or not. Sorry, when this problem prime is in P, and this K was I think 6. So K is 6 in this case. Yeah, so if you think about it, to see if a capital N is a prime number, the obvious thing to do is just go through all the prime numbers to the square root of capital N. Okay, so on the face of it, kind of looks like a polynomial time algorithm, but of course, going through square root of N numbers, square root of N is 2 to the N divided by 2. So this would be something exponential. So it was yeah, that was a major achievement. Okay, so the next class we're going to try and define is the following. Now, important types of problems are problems which, although we might not be able to find out if they're in P or not, at least we can check a solution very quickly. So let's just think of let's look at a few examples first. So so this is another problem which will be of extreme importance to us. Factoring. Okay, so this problem says given so you have to kind of like work this out. What is the decision problem? Because it has to be a yes no answer. So given a composite number n, does n have a factor less than f? that's a yes from the question. So that's a decision problem. So if someone claims it does, they can produce they can produce a witness, which will be a factor. So such a factor. And verify can verify B is a factor. It is getting polynomial time simply by division. Okay, so you can. We all know a long division algorithm that we were taught in pre-lab. Then we can verify the base cut polynomial by long division. So it are decision problems for which well, maybe polynomial. So the decision problem is a polynomial time verified for any instance of the problem, given any instance of the problem and a witness. Okay, so you can, so in this case, the instance of the problem will be a number m, and the witness would be the b, and the verifier can simply check to see if it is indeed in polynomial time a factor or not. Okay, so it will tell you straight away that it is not. So another one. So factoring is in. And another classical example would be subset. So here we have S is a subset of the integers. T is some integer. And we want to, the decision bias, does S have a subset? Which sums to T. Okay, so that's also in NP because the verifier is simply sums up all the numbers of the subset and sees if it's equal to, so let's say X, yeah? So the verifier simply sums numbers of X. So this is indeed also in NP. Hamiltonian is also in NP because the witness would have to be a Hamiltonian path, in which case you could check just by going through and checking that each edge in the path is indeed an edge of the graph. So this is Hamiltonian is also in NP. Okay, so as you all know, of course, P is contained in NP, since we can solve all problems in P. Solve problems in P in polynomial time. And the literally million-dollar question is whether they are equal or not. So whether there are problems in NP which are not in P. And for us, what will be very interesting is what are called NP-complete problems, and they are problems which, so NP-complete is a subset, or possibly, might be pairs. NP-complete. If there exists. Okay, so put it another way, NP-complete problems is a polynomial time reduction to solve any problem in NP. So in some ways, these are the hardest problems in NP. So the reason that factoring is important, so factoring And in its time prime, because it wasn't known until very recently, of course, that prime was in P, are interesting because they're somewhere between. We don't know they're in NP complete, and we don't know they're in P. Okay, so they're called NP intermediate problems. And we shall see that this factoring problem is going to come up later when we look at our quantum algorithms in detail. Okay, so I think I'll stop there for today. I will talk a little bit next week about a few more complexity classes and a few more famous problems. But you've probably got enough now to pretty much start all the exercises. So I will send out an email tomorrow with a list of all the different exercises. Okay, so you can have a go at your exercise, and please look at everybody else's exercises as well, and feel free to help each other. And we will. So as I said, the idea will be that that you could like knock together a PDF or a very neatly handwritten piece of paper, and we can go through it, and until we can get. Because normally I would have you out the blackboard and working in front of all of us. Okay, so we'll leave it there, and I'll see you all on Tuesday. Bye.
Goodbye.
Bye.